to trickle in here. Welcome to our kind of introduction to industrial and management engineering, particularly at Rensselaer. So welcome to our webinar here that we're having. We have one of our fabulous professors, Jen Pazor from Industrial and Management Engineering, that will be able to go over all the things that are, encompass that here. Kind of some housekeeping notes as people start to log in here. If you have any questions, feel free to throw them in the chat. I will be moderating the chat. It is a moderated chat, so when you submit a question, it doesn't automatically show up, kind of like if you're watching a streaming video game service. It'll populate one at a time as I kind of go through the questions here. Dr. Pazor does have some open-ended questions, so if you want to answer those in the chat, feel free, and I'll send those answers through as well. So at this point, I will pass it off to Dr. Pazor.
Well, hello. I'm really honored that you're spending some of your Monday with me. So I'm Jen Pazur. I'm a faculty member at RPI. And one of the things about me is I'm a huge fan of industrial and systems engineering. At RPI, you get a degree in industrial and management engineering. And it is, in my opinion, a fantastic field, but it is a field that not enough people know about. So first off, kudos to you for joining and getting aware of this. And so my hope is really to make this a little bit interactive. So if you have any questions, please throw them in the chat. I'm glad to answer them. In terms of just an agenda to kind of set up is, I want to just start with some motivating questions. A lot of times people don't really know what industrial and systems engineering, industrial management engineering is. And likely, if you're like me, I think it's a really good fit for lots and lots of people that maybe have not heard about it. So I'm going to ask some motivating questions and then talk a lot about what actually is this field. And then if we have time, some more introductions to myself as well. So I have a couple of set of questions. And just to give you kind of some setup is there is an A and a B, and I would like you to think about, would you rather do A or would you rather do B? And there is obviously no right or wrong answer to this, but I think it allows you to think about what are you interested in, and maybe if you're like me when you were in high school, you I think I want to be an engineer, but I don't know what to put in front. That is kind of the goal of these questions. And so my first would you rather, so would you rather A, try to understand the forces of an airplane wing so that you can make sure you design that wing to keep an airplane in the air. So thinking about, how do I make sure that I design this wing so basically the plane flies? That's option A. Option B is, would you rather, take the plane as an input? So you're not going to design the plane, but you're going to design all the systems and processes around it. So you would want to understand when you get there, I have this plane. Should this plane go from Albany, New York to San Francisco? Should it go from San Francisco to Dallas? Where should it go? Also, I have a lot of talent. I have pilots. I have flight attendants. I have data, I have passengers, and what happens if there's a hurricane and all of a sudden the flight gets canceled? How should I reroute things? How should I use information to make those decisions? And so in this situation B, you're not designing the plane, but you are still designing. You still are problem solving, but it's more at the facilities or the operations level. And so if you have some time, I would like you to kind of spend a couple seconds thinking about that. Would you rather design the wing of the plane, or would you rather have the plane and design the operations and the facilities and the schedules around, given you own this resource? Again, no right or wrong answer. So I'm going to pause there, and I'm going to give you another kind of would you rather. So my next would you rather is, you could think about, you need to design this stretcher. And so to be able to design this stretcher, you want to make sure if someone needs to use this, that it's sturdy and it stands up, right? So you would need to understand forces and loads, and making sure that if you put a patient on it, that this is stable. That's one option. So when you think about that, you are probably designing parts. You're making sure that the system is stable, is operable, moves, does all those kind of things. So that's A. B, on the other hand, is we still have that same stretcher, but now we aren't designing the stretcher. We might be buying the stretcher and saying, how many stretchers do we need? But also thinking about how should we design the procedures and the patient flow in a hospital to ensure, again, safety, but making sure that we're doing quick recovery, high quality medical care. And so what would you do here? You would think about, how should I design the process? Where should people be and resources be? How should I allocate them to ensure that we have the highest level of safety and the highest level of care there? And so again, just letting you kind of pause here, would you rather A, design the stretcher, or B, design maybe the healthcare facility, the operations, when they happen, where they happen, who does them? Hopefully you have some maybe preference for one of these versus the other. All right, so in terms of, all four of these problems are important. They're all complex. They're honestly all interesting, right? And another thing that's similar to all four of those situations is they all require math. They all require analytical skills. They would use computers to solve these things. They would use data. You can think about, though, the types of problems you're solving may be a little bit different, but they all use kind of these same somewhat fundamental skills of problem solving, data, computation, systematic thinking, right? So those are similarities. They're all critical. They matter to society. They matter to businesses. But there are some differences. So what are some differences in terms of these things? If you think about my example from, either the plane or the designing of the sketcher, they're usually a little bit smaller in scale, right? So you're designing the wing of the plane versus part B is thinking, okay, the plane is there and I'm designing the system and the operation around it. Similarly, in the healthcare example, instead of designing the part that goes into something, we are taking that machine, that resource, and then designing a bigger scope. And so one way to think about these two problems is, in some ways, the things in A, they're critical, they're important, someone needs to design them, but those are being inputs to a larger scale system in B. And another difference is how humans are viewed. I think the healthcare example is really critical in this, is that we need to think about the human, the person getting treated, as kind of central to our design of our system. And so I always say industrial and management engineers are the most people-oriented type of engineering. And some of that is because the problems we're really interested in are human scale, human problems. And we are using math and science to really design those things. And so there is no right or wrong answer, but I think thinking about what you prefer is useful in thinking about if you want to be an engineer, but you're not sure what kind of engineer you want to be. Engineers are problem solvers, they're designers. But what they design, what they problem solve about, are the words in front of it. And so if you liked A, maybe you should think about mechanical engineering, maybe aerospace engineering, potentially biomedical engineering. If you like the things in B, I think industrial and systems engineering at RPI, you get a degree in industrial and management engineering. Those are kind of the fields that fit. And so I put this out here as something is, I think a lot of people, when they think of engineers, they think about A. They don't always think about B. And so when you think about the world that we live in, COVID is a great example. Those are complex problems that have huge systems involved, that have huge interactions. We need the analytical math, science, computational skills to problem solve at that scale. And that's what industrial and systems engineers do. So what is kind of formally an industrial and systems engineer? This is my definition, but we design, control, and improve systems and processes. And as I'll show you in a video, my take is the things in purple are verbs. So those are verbs that describe what engineers do in general. So we design things, we control things, we improve things. And what are those things are really what goes in front of the word engineer. And so if you're thinking, I don't know, I like designing, I like problem solving, I like improving things, and you're not sure exactly what those things are, that's okay. I think you can figure that out as what type of engineer. And so how do we do this? We use analytical tools, and we really focus on making better decisions. And so here's a video.
Hi, I'm Jen Fazur, and I'd like you to consider a career in industrial and systems engineering. Please check out this video to see what the field is all about.
The role of an industrial and systems engineer is to design, control, and improve systems and processes. Design, control, and improve are verbs describing how engineers tackle problem solving. Industrial and systems engineers solve problems related to systems and processes. We do this by creating and applying analytical approaches to make better decisions. Systems and processes, and thus industrial and systems engineers, are everywhere. Our lab is the world, and Rensselaer's industrial and systems engineering graduates acquire core skills applicable to all sectors of society and enjoy a diverse range of career trajectories. They are found in supply chains, healthcare, manufacturing, logistics, entertainment, defense, consulting, finance, transportation, and even sports analytics and political analysis. Let's explore why. We are considered big picture engineers. We take a systems perspective focusing on the relationship and interaction between people, technologies, and resources. Industrial and systems engineers possess the technical knowledge to understand how systems function, what constraints limit their performance, where uncertainties exist, and how to quantify decision trade-offs. We are modelers. We optimize systems by integrating processes, data, and humans. We use data science, statistics, operations research, simulation, and computational methods to solve complex problems. We then use these models as our playground to plan, allocate, and utilize limited resources. Industrial and systems engineering is the most people-oriented field of engineering. We consider humans and human interactions central to the successful design and operation of systems. Industrial and systems engineering has a greater business orientation than other engineering disciplines. The list of CEOs with industrial and systems engineering backgrounds is impressive. All of these organizations have been led by an industrial and systems engineer, including companies like Apple, Walmart, and Accenture. These combination of skills make industrial and systems engineers in high demand. Graduates of our department enjoy a strong, consistent job market with above-average salaries. Rensselaer's industrial and systems engineers are able to think about problems analytically, to change complex situations into numbers and equations, into statistics, and into data-driven solutions. These transferable skills are demanded for our ever-connected and analytically driven world.
I'm a big fan of industrial and systems engineering. I hope this video helped you understand why. Please check out our department website for more information.
Okay, so hopefully that gives you a little bit of an understanding about what industrial and systems engineering is. One thing I will note is there is kind of a name problem in our field. So industrial engineering was kind of where it started. Where did that name come from? Is we started in kind of factories and thinking about the industrial side of systems engineering, but we've broadened quite broad. So there's now industrial and systems engineers in service industries, in policy, in sports, in anything. And so that's where the word and the field has kind of broadened. At RPI, you get a degree in industrial and management engineering. And I think that's interesting for something that was said in that video, is if you're really interested in business, but also really like math and science and kind of the data side of things, if you want to be a data scientist, if you've ever heard of management science, this is a really good merge between those. And so hopefully that gives you some context about what it is. And what I have kind of couple slides is to think about again, like, have you ever been in this situation before? And if so, I think that's a way to think about you would be a good industrial and systems engineer. And so my first one here is, if you've ever waited in line and you are like, this is really frustrating. I am really impatient. This is just not working. Honestly, your impatience, while people may say that's not good, that means you're a good industrial and systems engineer at heart. If you've ever thought about an experience and saying, how could this experience be better? That's a lot of what industrial and systems engineers do. So I think a good tagline would be, we design experiences. So some experiences are not as fun, standing in line at a shopping center, but you can think about making those experiences better. And how do you make those experiences better? Well, some of it is changing the design, the flow, the facility, the data, and some of it's resources, some of it's human, some of it's management. And so it's all of those different things are at our disposal to change and design. And so if you've ever been in one of these situations and you've thought about how to change this, industrial and systems engineering is something you can think about. Just to go back in terms of the math, there's actually a field within industrial and systems engineering known as queuing theory, which is the math of waiting in lines. And so you actually get a bunch of tools mathematically based to estimate things like, on average, someone would wait in line this much. The probability that someone would wait in line that's more than 10 minutes or less than 5 hours or something, you could calculate that. And so what I think is really cool about this field is we have a lot of the tool sets to go about designing experiences. And so we can use very analytical, quantitative data, computational tools to go and design new experiences. So that's one example. Another example of something you have maybe done is if you've ever interacted with your phone, and you were like, okay, I have to spend 5 different spots to get to what I want. If you're ever frustrated with the design and you're like, if this could have been moved over here, I don't understand how to use this technology. If you've ever thought about that, how you as a human or someone else that uses technology and how to improve it, you would make a great industrial and systems engineer. So this is a field of industrial and systems engineering, sometimes called human factors, ergonomics. And so it's the idea of how a human will interact with technology and making sure that it's usable and accessible by large populations of people. So if you like that, you would make a good industrial and management engineer. If you like planning things, so I'm actually a huge planner. So if you have ever, at your school been asked to plan a car wash or plan some event, and you think about, okay, all the resources that you need to make sure you have the right resources there. If you think about, okay, who's going to work which shift? How do you prioritize if I only have so many resources? What should I spend it on? And just making sure that operation goes smoothly. If you like that kind of thing, naturally you would be a good industrial and systems engineer. And so these are things you're probably doing, but we can actually provide nice what's called optimization methods to actually optimize so that you're maximizing your limited resources and you're making sure that people have the least amount of wait time and certain things like that. And so there are lots of cool tools that you can use to be better at this. But if you already like this kind of thing, then that's a natural intuition to go into industrial and systems engineering. The other thought is, if you've ever had to make a decision and you had to think about that decision in terms of many different trade-offs. And so a good one is, thinking about climate change and thinking about decisions that companies need to make. There's a thing called triple bottom line, where you want to make sure that you're making decisions that maximize economic, environmental, and social objectives. And honestly, most problems in this world have conflicting objectives. What that means is one of these goes up and the other one goes down. And so how do you decide how to make a decision? If you've ever thought about, hard decisions, some hard decisions are, what school do you want to go to? What do you want to major in, right? There are usually trade-offs associated with that. And so one thing I think that's actually really great about this field is, again, you get a lot of tools that, yes, make you good at your job, but also apply to many of the things you think about in your life. And it also gives you appreciation if you've ever had a decision made by somebody else that you were disappointed in. It gives you some appreciation that they may have constraints that lead to decisions that you didn't want to be made. But in the system that they're operating in, maybe that you can understand better why someone would make that decision. So we deal a lot with decisions, and there's actually a field within industrial and management engineering called decision analysis. And so how do people go about making decisions? How can we provide the right information to decision makers so that they are informed? And there's a lot of really cool stuff from a data analytics, but there's also a lot of really cool stuff from a psychology perspective. So if you're interested in management and psychology and how humans aren't always rational thinkers, and how does that influence how you want to present information? How does that influence how you want to design a system? These are all good things to have, and these are things industrial and systems engineers would do. All right, and then one kind of, I don't know, maybe you've seen this before, you look at this glass and is it half empty or half full? And, if you're an optimist, you would say the glass is half full. If you're a pessimist, you'd say it's half empty. And as industrial engineers, we'd say the glass is 50% bigger than it needs to be. Okay. And so when you think about industrial and systems engineering, we really think about there is something we need to accomplish, and then we need to gather all the information, the resources, the humans together and design that system for what it needs to do. And so I think we're really good at setting objectives, and we're saying we're going to meet those objectives, but we have limited resources to do that. So building this glass twice as big, maybe that's not the best answer. And so I think that's one thing that's also pretty cool about our field is we think about what are we trying to accomplish, and then how can we get there? And so you should be creative. You should think outside of the box. There isn't just an answer. It's not like calculus or algebra where there's an answer at the back of the book. There are many different answers, and you use all these tools to get there. All right, so those are kind of some examples of things maybe if you like to do, you would fit well with industrial and management engineering. So then you can think about, okay, well, what does industrial management engineers do? Where do they exist? So this is a slide that basically shows where a lot of our alumni go and take jobs. And so one of the things to note is that there are systems and processes literally everywhere. So if you're an industrial management engineer, we design, improve, and control systems and processes. That means every single company you could ever think about really should be hiring one of us. And likely all of these are. One of the struggles, and I have some slides later about this, is they're not always called industrial and systems engineers. They may be called different things, but they have a degree in industrial management or industrial and systems engineering. And so, there's lots here, and that's by design. You can think about, Walt Disney World hires a ton of industrial engineers. What do? They literally look at and say, how long are lines going to be? How can I design the process, meaning the waiting process, so that people are having fun while they're there? They're also forecasting demand. So what does that mean? They're trying to predict how many people will show up at the park every year, but also at individual places within the park. And so there's a lot of data associated with that. They're also building really complex what's called simulation models to say, how do I make sure when I design a new ride that the wait line is not just crazy? How many different roller coaster units do I need to ensure that this is a viable ride to add, and so forth. There are lots of companies on here that are consulting companies, and a large portion of our undergraduate students get jobs in consulting. Accenture is an example, Deloitte, some of Ernst Young, and then those are like consulting companies where you go and be a consultant. ZS Associates is another one. And then there are a lot of people that go and work for more traditional Fortune 500 companies, but they serve as kind of an internal consultant. And so if you're interested in being a consultant, I think industrial engineering is a really good field for that. Why? Because ultimately we are modelers. We model complex systems and problems, and then we personalize the solution based on an individual client's data. But one of the things you take away from a degree in industrial management engineering is that a lot of the decisions and a lot of the problems have a similar structure. So they're assignment problems, they're scheduling problems. And so you get this structure in your head, and then what you're able to do is you go to a client site and you personalize that solution using their specific data. But a lot of the ways you're thinking about the problem you've seen before. And that's a lot of what consultants do. They have a model for the problem that they have there, and then they personalize it for each of the different entities. Some other places you see here are things that are more manufacturing or supply chain. So Gore, they're a high-tech company. Is an example. Nestle would be food manufacturing. Then there's like Target and like L'Oreal. You have a lot of these industrial and systems engineers working in supply chains. So understanding and making sure you have the right product at the right place at the right time. Pricing, a lot of those kind of business decisions are made now using quite sophisticated algorithms, optimization, data, and these are things that we learn really strongly. And so if you think about core engineering classes, one of the core engineering classes for our discipline is probability and statistics. And so probability and statistics allows us to understand for example, buying patterns, price, so shopping, demand, and then if we know probabilistically and statistics, we can then do trade-offs of how much inventory we want. And so a lot of this is becoming quite sophisticated, and you get a lot of those skills in our curriculum. There are also a number of companies that are hiring industrial and systems engineers that don't call them industrial systems engineers. And one of those is in healthcare. So if you're actually interested in thinking about quality control, patient safety, process improvement within any healthcare facility, a lot of industrial management engineers get hired to do that. There is also a lot of quants in finance that get hired in a background, again, of stochastic processes, which is a probability and statistics kind of foundation. And so really, my mentor used to say, any company, they all are hiring some sort of industrial and systems engineer because they all have systems and processes. So, okay, so, they're all over the place. So what do they actually do? Okay, so one of the things that they do is they really take a big picture perspective. So there is some need at the center, and then they really look at how can I meet that need? And what I think is cool about that is they think about very different ideas. They combine people. So people are talented resources. They're creative. How should I best use that resource? Hence the name management on there. They also use computers. They use data. They use the fact that you have limited resources in terms of money. And you really take these and integrate them to meet whatever need that is. Okay, so that's very general. Let's take maybe a little more specific example. So one specific example may be in a healthcare facility. And the question is, how many beds are needed in the emergency department of the local hospital to reduce the time spent in the waiting area? And so if you think about this problem, you could think about, okay, one way to think about this is, okay, I have currently 3 beds. I could literally go and knock down a wall and put up a 4th bed and measure some things and see how that went. I could also take away a bed and go do that and measure that. That's obviously not probably a good idea. Why? Well, first of all, that's very capital intensive. It's very disruptive. We also don't know, that's also maybe some ethical things. You're taking away a bed and now we have really bad patients waiting in the waiting room and potentially people have very bad health outcomes, right? So there are lots of reasons why that's not a good idea. And so what I think is really cool about industrial and systems engineering is we get this toolkit of ways to solve this problem without all of those problems. One of them is called simulation modeling. And so what this is you build a computer software that actually is like a simulation. So if you've ever played like SimCity or something, it's similar to this in the sense that you're simulating what you think will happen. But the backbone of this is probability and statistics. And so you use the probability that somebody will show up at a certain time. How long does it take? It doesn't always take exactly 10 minutes. It takes sometimes 10 minutes, sometimes 5 minutes, sometimes 3 minutes, and so you incorporate all of that into a simulation and then you push go. And a lot of the simulations give you statistics, which is what I'm kind of showing on the bottom there. They also give you really cool animations. And so you can actually build that, and then you can do what-if analysis. You can say, okay, if I have 3 beds, we have this time in the system. If I have 5 beds, we have this other time in the system. You can actually see people waiting, and you have a lot of good animation. So it's a nice merge between computers, if you like programming, computer software, and statistics and business, right? So it's allowing you to do, if you're in the analytics world, descriptive analytics. So you're describing what you think will happen, and you can change scenarios and get some understanding. And so in our curriculum, you would take a whole class on just simulation modeling. You would also take a class on probability and statistics, multiple classes. And so those are kind of the foundations that get plugged into simulation modeling, for example. So that's one example of this. Another example is you could think about, okay, how do we do this? So you can think about mathematical modeling. So one thing that industrial and systems engineers do is you think about what products should be displayed in what stores. You think, okay, that's simple, right? You just say, okay, I just think we should have this set of products. That's actually a very, very complicated problem because of all the interactions, right? So let's say I have only one type of sunglass. If I now add a second one, it's not true that the sales will just go up by twice. There might be cannibalization, meaning if I put 2 of them, you pick the one you like, and actually sales go down on certain ones. Also, if you have too many choices, maybe people just get overwhelmed. And then if you have more choices, you have to think about the supply chain behind this, right? And so each time someone buys something, in theory, it should be replenished. So you should get an order from somewhere else in your supply chain. And thinking about all of that is actually a very challenging problem. And so how do you go about this? One way you go about this is probabilistically. So you don't know exactly what someone's going to go buy, but you might know some probabilistic information. What is the probability someone buys this given that you have this assortment of products? And so you can think about doing some pretty sophisticated mathematics to figure out, we want to maximize expected revenue. And how do I do that? By determining what types of products do I put there. So that's an example of this. Inventory management is kind of the more general term, is how much do I have where and when, and how do I place orders? And so there's a huge mathematical background behind that. You take a whole class in our curriculum on supply chain management. I actually teach that course, so I'm biased, but it's fun. And so that course is one where you use a bunch of math, statistics, and computational tools to answer questions around the supply chain. So how do I determine where to locate facilities? How many facilities should I have? What should they store? How should I predict demand? How do I determine labor? How much do I have, where, and when? All of them using, quite sophisticated, for the most part, simulation, optimization, and probability and statistics. So those are kind of business examples. One thing I want to say is there are lots of industrial and systems engineers that work in public policy. One of the reasons I think we fit really well in public policy is we deal well with uncertainties and we deal well with trade-offs. So unfortunately, in a lot of public sector problems, there are limited resources. And so resource allocation is not obvious. I'll pick on a little bit the computer science scientists here, is they also deal with a lot of these types of problems, but a lot of times they don't consider the limited resource aspect of things. So they'll do a lot of jobs of like estimating ratings. And so they're really, really good at that. But then when they go to make a decision, they have all of the ratings estimated. We need to decide, okay, I would love to give everybody malaria insecticide. Unfortunately, we don't have enough of that. So we have to prioritize who gets it when. And this is an actual problem that some industrial and systems engineers, actually at Georgia Tech, worked with the World Health Organization to think about, when is the transmission season? How should I deploy limited resources? How should we allocate them? And honestly, the math is the easy part in this problem. What is hard is, how do I measure what's a good solution? Is the right objective to maximize the number of people treated? You may say, oh, that seems great. But actually, that might not be the right answer, because none of the people, they only serve one region where there's maybe high density, and nobody else gets served over there. So it might be a very unequitable allocation. And so what I think is also super cool about our field is we really are equipped to tackle a lot of these really hard societal problems where there's not a clear answer, but we want to use our resources in the best way possible, and we want to do the most good. And so there are hard questions about what do we mean by most good. And I think there's not necessarily a right or wrong answer there, but we have the math and the data to support. If we're going to make a decision, we should use the resources the best we can. So that's an example. Another kind of public sector example is in logistics response. And so you think about a lot of the things that industrial and systems engineers do is they do them and everything is great when it's working. And then the minute something goes wrong is when you see really the value of what we do. And I think COVID-19 is a good example. You've probably never heard the word supply chain so much in your life until there was no toilet paper available or there was no water available in a hurricane. And so what we are able to do is we are able to try to utilize the human and the human decision maker and making sure that they are agile in their decision making. So this is an actual problem some of my colleagues in my department worked on, is they created a software system able to alert where are needs when a disaster hits, and having visibility into the needs is kind of step one. And then after step one, we then need to allocate these limited resources, and we need to think about how to do that in an efficient manner, but also in an equitable manner. And so computer systems can really augment human capabilities. And so I think we are usually very human-centered in our design, but we realize that computers, technology, data really can help us do this better. And you may say, okay, that's easy. You just build the computer system, you get the data, whatever. These are actually really complicated problems because of interdependencies. And so I think one of the things we really do well as industrial and management engineers is we think about the system and we think about these connections between multiple other systems. And so an example of this in the hurricane, and some of my colleagues actually do research and are leading experts on this, is if you want to make sure you get somebody delivery of food in a hurricane, for example, it's not as simple to just say, send water to that house. Why? Because oftentimes there's a tree down. So the tree first needs to get cut, then the power can come back, then we can think about transporting something on that road, right? And so if someone just says, yeah, just send the shipment, you miss a lot of the nuance, a lot of the complexity. And so by taking a systematic, a big picture engineering perspective, we are able to address and use resources much more efficiently. And the other thing I would say is we're not doing this alone. We need electrical engineers to decide how to repair the power system. We need civil engineers to help decide how to get the water and the waste system back. We need sociologists to understand the dynamics going on in the communities. We need et cetera, et cetera, et cetera. And so I think we are the integrators of all of this, and we are sometimes the glue between all of these things. And so if you like math and science and thinking about complex problems, this is a really good field to make a lot of impact, whether that's in the public sector or private sector. There's lots of opportunity. I know I've been talking a lot. I want to just say one other thing about kind of this field is really what's changed, I would say all of engineering, but specifically our field is data. And so if you've ever wanted to be a data scientist, there are lots of paths to that. One of those paths would be industrial and management engineering. And what I would say the difference, there are different ways you focus on different things, but we really focus on decision making. So we have the tools from a computational statistics, optimization analytics perspective, as well as the domain knowledge that really relates to decision making. And so this is a graphic that I just found on the internet talking about the modern data scientist. And, you know, oftentimes, actually my husband, who's also an industrial engineer, is a data scientist. And he's a data scientist in video games of all places, but like he talks about there's a lot of times people have a hard time finding data scientists because they're somewhat a unicorn. They need to know math and statistics. They need to know programming and database. They also need to have domain knowledge into whatever you're providing insight in. And you also need to be able to communicate whatever these insights are to a larger group. And so there are different fields you can go into to become a data scientist, but I feel like industrial management engineering is one, and it's a really good holistic one. We do all of those things. So in terms of math and statistics, just in our curriculum, you have to take a required course on modeling and analysis of uncertainty, statistical analysis, operations research, which is prescriptive analytics, simulation. Those are all required. And then you can also take other courses that would fit technical electives in terms of additional math and statistics. So we're very math statistics heavy. But then we don't stop there. We also think about the domain knowledge. So we think a lot about operations and supply chains. But other domain knowledge as well, but those are the most obvious ones. And so we have a lot of kind of business sense on the management side and supply chain and operations management side. And then we also take some database programming. And I would say out of the three of those, these are the ones we do some and we're getting more and more into just as the world is getting more and more computer heavy. But probably would say the weaker of the three. But you do have to take Comp Sci 1. You also have to take information systems, which is, SQL, getting data out of databases and using it. And then there are some students that will minor in Comp Sci or take technical electives that support that. And then a lot of our courses also incorporate a lot of computer science. One thing I will say is I do computer science coding for my research. I'm not a computer scientist. What I like about computer science is the algorithm, the logic, thinking about here's a hard problem, how do I break it down? How do I get the data I need to make these decisions? So I think knowing how to code is useful, but it's different than being a computer scientist. My code is maybe not the most efficient. I really hate trying to figure out how do I make sure this file sees this other file? I'm not really I don't know how much RAM my computer has, right? I use computers as a tool to do a bigger thing. And I think that's a way to think about it. If you want to code and you really, really care about the design of your computer, okay, go to computer science or computer engineering. We used coding as a really powerful tools to help make decisions on really important problems. And so if you don't love coding, I think that's still okay. You can still be an industrial engineer. If you like it a little or you find it as a tool to use, that's also good. And just to illustrate, and then, communicating and visualizing, I'm totally biased, but industrial and systems engineering is something that I think we're the most people-oriented. If you like people, you can still be an engineer, and you should be an industrial and management engineer. So we really do a lot of that. And at RPI in particular, I think they do a really good job of these what's called professional development and skills thinking about kind of the broader side of things. So I won't put this up here for the detail, but I want to say one of the reasons to give us some more evidence, if you want to be a data scientist and you're thinking about going into engineering, at RPI, we just launched last year a minor in data science and engineering. So you can actually minor in this without being a major in industrial and management engineering. But it also illustrates that a lot of the courses that are required for this minor are required for our degree. And that's because data science is one of the many paths you can take as an industrial and management engineer. And so, I don't know, Greg, are there questions people have? That I can keep chatting, but if there are questions.
Yeah, I'm not seeing any specific questions. Again, if you have any questions for Jen or myself from the admission side, feel free to ask. We're here as long as you need us. This is a lot of great information. Again, I always think industrial is one of those areas that a lot of students seem to transfer into once they're at RPI. We seem to bring in a smaller number than those that actually graduate. So you guys are doing a great job when it comes to that. So yeah, if you have any questions, feel free to send them through. I'm not seeing any questions right now, but if you want to keep, I got one. Perfect. If you could recommend a coding language for aspiring industrial engineers,
so I would say there's multiple. I don't think it's super important what specifically it is, but R and Python, I would say, are the most obvious ones. And so in my class, for example, I teach a supply chain design. We use R, and some of the data science stuff would use Python. What I think is more important is that you kind of understand the logic of coding. So if you go and learn C++ or whatever, you'll be able to pick up the stuff that we need. And I would say more than a computer scientist, we don't care as much about the efficiency of the code. It's more about the logic. But R is great, just as a background, is it started actually by a bunch of statisticians. So it's really good at probability, and it has very nice packages, which is a foundation of our field. So I guess if you haven't started, I'd recommend R or Python.
Yeah, I'm not seeing any more. Oh, perfect. He says thank you. Ryan says thank you. So if you want to keep going, you can. I know you've hit a ton of information.
Well, maybe I'll just end. I'll jump kind of here. Is, I started off at the beginning kind of asking about these different things. And I think, honestly, I mean, I'm super biased, but I think industrial and systems engineering is a fantastic field. But it is something people don't always know about. And I mean, so when some people think about, okay, what's different about us? Is I think we're bigger picture, so we're systematic. That goes back to my wing on the plane versus the plane. So we care about the plane as the input, not designing the wing on the plane. And I think that's something some people love designing and thinking about, free body diagrams and physics, then you should definitely go be an aerospace engineer. But if you're like, I'm interested in mathematically thinking about things, if you've ever done these logic puzzles where you're like, the person in the yellow house lives next to the person that has a parakeet, and this person has 3 kids, who lives in the house next to Jill or whatever, those types of things, if you like those are basically industrial management engineering, right? So we could actually mathematically formulate that problem and tell you the answer to that. But if you have that kind of skill set of thinking through, okay, if this, then that, and what's going on, I think you would make a good industrial and systems engineer. Also, I would say from a people orientation. So like the word management is in our degree. And I think so you're required to take a management elective from the business school. There's a little bit more integration between human interaction and business orientation. So if you want to go start your own business or be a CEO, go be an engineer, and then you can do everything a business major can and plus more. I would say on that. And so I really think thinking about us is a good integration between those. And the other thing I'll say, I know I said it was the end, is the world needs more of you. So this is from the labor statistics. Is all engineering has a good outlook, but if you can see at the bottom, engineers in general growth 5%, industrial engineers have 8% growth. So, I mean, I know in COVID and crazy economic times we're in, it is a good field to go in. So I will just end with my contact information to also say, I'm an associate professor. I'm also the undergrad curriculum coordinator in our department. So if you have questions about our curriculum, I'm the person. I also maintain a blog. I'm on Twitter. I'm on LinkedIn. Feel free to add me to any of those. Send me an email. Also, our webpage for our department is also listed on here. So if you have anything, there is a good source. But feel free to reach out via email if you have any questions.
Yeah, absolutely. And again, I'm always thinking about kind of who is in industrial engineering, and we just had one of our lead student ambassadors, Mackenzie Lard, who graduated as an industrial engineer. She came in as, I believe, as a biomedical engineer and changed. She just got a job at Deloitte. So she was supposed to start in September. I'm not 100% sure with COVID how that's going to work. We do have one question for you. At Rensselaer, are students able to work with professional industrial and systems engineers in internships? So again, I know, for example, Mackenzie did an internship at both Hasbro and Deloitte as an industrial engineer, and she took the job at Deloitte that followed.
Yeah, so a couple things.
Elaborate
yes,
on that
and I would say most of our students do internships, co-ops with the way semester in the Arch. There's no huge problem finding them. They even now in COVID, one of the students I'm working with is at General Electric, and another one is at GM, the car dealer, and they're actually able to work remotely. So yes, there's all kinds of internships in this area. Regeneron hires a bunch of our students for internships. The consulting companies, so Deloitte, like Mackenzie is headed there. ZS, which is a consultancy that's a little bit more focused usually on pharmaceuticals, hires a bunch of our students. And then a lot of the supply chain companies. So Gore Technologies, a number of our students, I was just talking to them this summer, are there even remotely. Caterpillar, Procter & Gamble, they all do internships, co-ops. John Deere, UPS, FedEx, all those kind of things. And then I will also put a plug. There are many, many wonderful industrial engineering departments across the country. One thing I think that's a little unique about RPI is undergraduate research. And one reason I ended up at RPI as a faculty member, I was a faculty member somewhere else, is that there's this unique value of undergraduate education and a research institution that is not as common as you would think. And so I really like undergrads. I like teaching them. I have a bunch of them in my research lab. So I wrote a paper with a recent, journal paper with undergrads, but that's valued in a different way than I think some universities that are, big R1 universities that are really focused on PhD students. I have PhD students as well, but there's this unique kind of intersection between having research and having a focus on undergrads that I think is a cool opportunity if you're interested in that. So.
Awesome. I'm not seeing any questions. I have put my email in. I put Jen's email in there as well. Sometimes the clicking on the chat works a little bit easier if you just want to click it and it goes right to the Gmail or Yahoo email, whatever you might be using. So my email is in there. Jen's email is in there. So if you have any further questions or you didn't feel comfortable asking a question here to us over the chat, feel free to email us at any time. I'm still not seeing any questions, so we'll wrap up here. I want to thank Jen for presenting and telling us not only about industrial engineering, but industrial engineering at Rensselaer. So thank you for joining us tonight. And I want to, perfect. Thank you. Lots of thank yous from the chat here. So again, thank you for joining us, taking some of your Monday evening. So everyone stay safe and enjoy the rest of your week.